Test and repair are non-value-add operations. Defective products should not be produced in the first place. Unfortunately, the state-of-the-art in many processes is not there, so tests and controls need to be part of the value stream. Ideally, as the value stream becomes more robust, some of these controls can be removed. In the meantime, we need a test and repair plan, if repair is possible. A test/repair loop can become a bottleneck for the whole value stream when test first pass yield is lower than planned. This is a model of a typical test and repair loop. There is a buffer before the test operation and another before repair for the units waiting to be tested or repaired. Units passing test OK leave this loop to continue the value stream. Those failing test go to repair, and after repair, they need to be tested again.
A drop in first pass yield is, usually, caused by problems upstream in the value stream. Test and repair loops are often absent in value stream maps, despite the potential to become the bottleneck for the total process. Download this Excel example file testrepair.xlsm to your PC from OneDrive folder Polyhedrica. You must close all open Excel files before you open this one, and you should enable macros.
You need a test and repair loop in a value stream to detect and repair defective units. The objective is to detect defective units as soon as possible to minimize the impact. Defects are typically produced upstream in the process. The critical metrics of these operations are test and repair capacities and test first pass yield, which depends on the quality level of the units received. Repair capacity has, typically, high variability, so we need to know the repair standard deviation. The main objective is to ensure that this test/repair loop doesn't become the bottleneck for the whole value stream. This means that output throughput should be equal to the input. Enter your values in the yellow cells. To run the simulator once, press F9. Press Ctrl+R to put all work in process to 0 and set the default values. To run 100 cycles, press the Run 100 button.
This test repair loop is part of a value stream with a throughput of 100 units per hour, takt equals 36 seconds. You need to work out the minimum required test and repair capacities to deliver 100 units each hour. The ideal case is when first pass yield equals 100%. In this case, no repair is necessary, and the required test capacity is just 100, which corresponds to the value stream takt time. Let's assume 1% of the units are failing test first pass yield equals 99%. The immediate result is that the output of this loop drops to 99, it has become the bottleneck of the value stream. Since we are not repairing the faulty units, they are accumulating in front of the repair station. How much test capacity do we need in this case? We can calculate this without the need for simulation. In this case, when we test 100 units, only 99 come out OK, we have multiplied 100 by 0.99. If we need an output of 100 items OK, how many do we need to test? Answer, we divide 100 by 0.99, which gives us 101.1. So, we need a test capacity of 101.1. And the repair capacity will be 101.1 minus 100 is equal to 1.1 units per hour.
With the calculated test and repair capacities, we can balance the loop and deliver 100 items per hour.
Test time typically doesn't have much variation, especially if it is automatic. Repair time, on the other hand, tends to have high variability. Some automatic testers may provide specific repair instructions, but very often repair requires an investigation which might take a long time. Let us assume that in our example an average repair capacity of 1.1 items per hour has a standard deviation of 0.5.
Let us assume that repair capacity follows a normal distribution.
We see that occasionally output will drop, and a queue will develop waiting for repair. This means we will need additional average repair capacity to compensate for this variation. Let us increase the average repair capacity to 2 units per hour. Now there is no waiting for repair queue. But now we have a queue in waiting for test. But it is not increasing, and the output is maintained in 100.
Use the Run 100 button to see the dynamic behavior. Due to the repair time variation, we see an accumulation of WIP before test and before repair. WIP accumulation before test is protecting the test operation from the repair variation. When this buffer is empty, we will miss deliveries to the rest of the value stream. Output drops below 100. This will cause a problem further along the value stream. We can reduce the frequency of these missed deliveries by increasing test and repair capacity, but this will involve additional cost.
Imagine that test first pass yield drops to 98% due to a problem upstream, maybe a supplier. To run 100 iterations, press button Run 100. We will need additional test capacity to also test again the repaired units. The standard deviation of the test capacity will typically increase also, and this will cause an accumulation of work in process, both before test and before repair. This increase of WIP will increase the overall lead time of the value stream. The test repair loop should, normally, be included in the value stream map because they are critical steps in the process, which could become the bottleneck of the total value stream. In this value stream map, we can see the effect of a functional test first pass yield of 80%. A 19% additional repair and test capacity is required to meet the takt time. And the side effect will be an accumulation of WIP of 13 units before repair and 66 units before test. This excess WIP will cause a 4-hour increase in the total lead time.
In these videos you can see how a test and repair loop is included in a value stream map. You can experience the different effects with an Excel simulator.
These are some conclusions. A drop in test first pass yield should trigger immediate actions to analyze and correct the source of the defects, avoid producing defects on the first place. In the meantime, we will need additional test and repair capacity to meet the value stream takt time. The repair operation may require high skills, which are typically in short supply, so enough training should be provided to ensure it doesn't become the bottleneck for the total value stream. By developing a robust repair process, we can reduce the average repair time and its standard deviation, reducing this risk. The repair operation should provide a Pareto of defects, which could be traced back to their origin to avoid producing them on the first place. Test and repair do not add value, so the objective should be to reduce them and eventually discontinue them if possible.
See this article in polyhedrica.blogspot.